Welcome to space science. The universe looks calm in the night sky, but its true size is almost impossible to hold in the mind. Beyond Earth, beyond the solar system, beyond the Milky Way, space opens into distances so vast that even light needs billions of years to cross them. In this video, space science journeys from the moon to the galaxies, from the cosmic web to the edge of the observable universe, asking one quiet question: how big is it, really? Before we begin, please like the video, subscribe to Space Science, and turn on notifications so more deep space documentaries can keep coming. The universe, as it is known, begins at a boundary that is not a wall but a limit set by time and light. This boundary is called the observable universe. It forms a sphere centered on the point from which observation takes place, and for Earth, that point lies within the Milky Way galaxy. The observable universe includes all regions from which light has had enough time to travel across space and reach the present moment. Beyond that boundary, space may continue, but no signal has yet arrived. The limit is not fixed in a solid sense, but defined by the age of the universe and the speed at which light moves. Light travels at a constant speed in a vacuum, covering nearly 300,000 kilometers in a single second. Because the universe has a finite age, estimated at about 13.8 billion years, only light that has been traveling for that duration or less can be observed. This seems to suggest a boundary at 13.8 billion light-years. However, the situation is more complex. Space itself has expanded during the journey of that light. As a result, the regions that emitted the earliest visible light are now much farther away. The present distance to the edge of the observable universe is estimated to be about 46 billion light-years in every direction. This expansion of space is a central feature of the universe. It does not occur as motion through space in the ordinary sense, but as the stretching of space itself. Galaxies are not flying outward from a central point in a fixed void. Instead, the space between them increases over time, causing distant galaxies to recede from one another. The farther a galaxy lies, the faster it appears to move away. This pattern is described by what is known as cosmic expansion. Observations indicate that this expansion began in a hot, dense state and has continued ever since. The observable universe, then, is shaped by both time and expansion. Light from distant regions begins its journey when those regions are much closer. As the light travels, the space it crosses stretches, increasing the distance between its origin and its destination. By the time the light arrives, the source has moved far beyond its original position. This means that the observable universe includes objects whose current distance exceeds the distance light has traveled. Within this vast sphere, matter is not evenly spread. Large regions contain galaxies, clusters, and structures, while other regions are nearly empty. Yet even the emptiest regions are part of the observable whole. The boundary itself does not mark an edge of existence, but a limit of information. Beyond it, the universe may continue indefinitely, or it may have a larger but finite extent. Observations cannot yet determine which is correct. The idea of a horizon helps describe this boundary. Just as the horizon on Earth marks the limit of visible land or sea, the cosmic horizon marks the limit of visible space. However, unlike a terrestrial horizon, this boundary is not fixed by position but by time. As time passes, more light from farther regions has time to arrive, and the observable universe slowly grows. Yet this growth competes with expansion. Some regions move away so quickly that their light will never reach the observer. No matter how long time passes, The size of the observable universe is therefore both immense and limited. It contains hundreds of billions of galaxies, each with billions or trillions of stars. The distances between these galaxies are measured in millions of light years, and the distances between clusters stretch even farther. All of this exists within the region defined by the cosmic horizon. Measurement of such distances relies on careful observation of the light. Astronomers study the stretching of light waves, known as redshift, to determine how fast objects move away. Greater redshift indicates greater distance. By combining these measurements with models of expansion, the scale of the observable universe can be estimated. Observations from space telescopes and ground observatories continue to refine these values. The observable universe also reflects the conditions of the early cosmos. Light that has travelled for billions of years carries information about the state of matter and energy at the time it was emitted. By observing distant galaxies, astronomers effectively look back in time. The farther the object, the earlier the time seen. This creates a layered view, where distance corresponds to age. At the outermost reach of observation lies the earliest detectable light, a faint glow that fills all directions. This light marks a time when the universe became transparent, allowing photons to travel freely. Before this moment, the universe was opaque, and light could not move far without scattering. The boundary between opacity and transparency sets a natural limit to observation. Despite these limits, the observable universe provides a coherent picture of cosmic scale. It reveals a universe that is vast beyond ordinary comprehension, yet governed by consistent physical laws. Its size is not defined by a physical edge, but by the interplay of light, time, and expansion. The boundary is a horizon of knowledge, not a wall of matter. As observation improves, this horizon may shift slightly, but its fundamental nature remains. It is the largest region that can be studied directly. Everything within it forms the known universe, while everything beyond remains uncertain. The true size of the universe, if it has a size at all, extends beyond this horizon, hidden from direct view. Within this immense sphere, the structure of the universe begins to emerge. Shaped by gravity and the distribution of matter, patterns form across enormous distances, linking galaxies into networks that stretch across space. These patterns lie well within the observable boundary, forming the next layer of understanding as attention moves inward from the farthest visible edge. A faint light fills the whole sky. It does not come from stars, and it does not belong to any galaxy seen by the eye. It arrives from every direction with nearly the same strength, and for that reason it seems at first like a smooth sea of radiation, quiet and even. This light is called the cosmic microwave background. It is the oldest light that can now be observed directly. It comes from a time when the universe is very young, long before galaxies, planets, or living things appear. In this light, the early universe leaves behind its broadest visible imprint. The cosmic microwave background begins as ordinary light in a much hotter universe. In the early age, space is filled with an intense bath of radiation and matter packed together at high temperature. Electrons, which are very light-charged particles, move freely. Protons, which are the cores of hydrogen atoms, also move freely. Light cannot travel far through this environment because photons, the particles of light, scatter again and again from the free electrons. The early universe is therefore not transparent. It resembles a glowing fog in which light is constantly redirected. As the universe expands, it cools. The drop in temperature does not happen in one place first and then another. It happens everywhere at once because space itself stretches everywhere. After about 380,000 years, the temperature falls enough for electrons to combine with protons and form neutral hydrogen atoms. A neutral atom carries no overall electric charge, so it interacts far less strongly with light than a free electron does. Once most electrons become bound into atoms, the fog clears. Light is no longer trapped in constant scattering. It begins to travel freely across the universe. That release of light is not an explosion or a flash from a single point. It is a change in the whole young universe. Every region becomes transparent, and photons set out in all directions. Those same photons still travel today. Over the immense passage of time, their wavelengths stretch as space expands. Light that begins in a hot visible or infrared range becomes longer and cooler until it reaches the microwave part of the spectrum. Microwave means a form of light with wavelengths longer than visible light and shorter than radio waves. Human eyes do not see it, but instruments can detect it with great precision. Because this light has been travelling since the universe first becomes transparent, it offers a direct view of that early time. It does not show the first instant of the universe, and it does not reveal the era before transparency through direct sight. Earlier conditions must be inferred from theory and from later traces, but the cosmic microwave background does show the universe at the first moment that light can move freely over long distances. In that sense, it forms a surface of last scattering, meaning the last time the photons are scattered before they journey almost undisturbed across space. This ancient light is remarkably uniform. Its temperature is a little above 2 degrees above absolute zero, almost the same in all directions. Absolute zero is the coldest possible temperature, where ordinary thermal motion reaches its minimum. The near evenness of the cosmic microwave background shows that the young universe is extremely smooth on large scales. Matter and energy are distributed with extraordinary regularity, yet the smoothness is not perfect. Tiny variations appear from place to place, with differences of only a few parts in 100,000. These small irregularities matter greatly. In maps of the cosmic microwave background, the slight differences in temperature reveal slight differences in density in the early universe. Some regions contain a little more matter, some a little less. Gravity acts over time on these tiny imbalances. Regions that begin denser pull in more matter and grow. Regions that begin thinner give up matter more easily and become emptier, much later. These very small early variations help lead to galaxies, clusters, and the larger structure of the universe. The background light therefore records both smoothness and the faint beginnings of all later cosmic form. The pattern of these variations also contains information about the contents of the universe. Observations indicate that ordinary matter, dark matter, and radiation all leave measurable effects in the early plasma before transparency. Dark matter refers to matter known by its gravity but not by emitted light. It does not scatter photons the way ordinary charged particles do, but it contributes to the pull that shapes density patterns. The early plasma supports pressure waves, often called sound waves, because matter and radiation push and pull against gravity. These waves leave a subtle spacing in the pattern of the background light. By measuring that pattern, astronomers estimate the age, composition, and geometry of the observable universe. The geometry is especially important. Geometry here means the large-scale shape of space. Observations of the cosmic microwave background indicate that the observable universe is very close to spatially flat on large scales. Flat does not mean empty or two-dimensional. It means that, across immense distances, space behaves in a way that matches ordinary geometric expectations more closely than curved alternatives. This result places strong limits on possible overall shapes, though it does not by itself determine whether the full universe is finite or infinite beyond observation. The background light also shows that the early universe is not chaotic in the everyday sense. It is hot and dense, yet governed by order that can be measured. Its small variations follow patterns that agree closely with the standard picture of cosmic evolution. Observations from satellites such as COBE, WMAP, and Planck refine this picture over many years. Each mission maps the ancient light with greater precision and reveals more of its delicate structure. The overall result remains stable. The young universe is smooth, slightly mottled, expanding, and already carrying the seeds of later structure. There are still uncertainties. Observations indicate a broad and successful model, but some measurements leave tensions in detail. The exact rate of present cosmic expansion, for example, is not measured in perfect agreement by all methods. The cosmic microwave background contributes one route to that value, by linking early conditions to later expansion. Other methods use nearby stars and galaxies. The difference remains an active area of study. Even so, the background light stands as one of the strongest foundations in modern cosmology. This sea of ancient radiation is not merely distant, it is surrounding. The same old light passes through the space around Earth at every moment, a cooled remnant of the early universe still present today. It is quiet, nearly uniform, and immeasurably old in human terms. In it, the young cosmos appears not as a blaze of separate objects, but as one vast luminous field, just beginning to let light go free. Between the oldest visible light and the great structures that later form, the universe is dominated by distance. Most of its volume is not filled by stars or glowing clouds or bright galaxies. Most of it is space with very little in it. This emptiness is not absolute nothingness. A few particles pass through it. Radiation crosses it. Gravity extends through it. Dark matter is present within it. Yet by ordinary standards it remains almost unimaginably empty. If the universe seems full in photographs, that impression comes from how light gathers around rare concentrations of matter. The larger truth is quieter. The universe is mostly interval. This becomes clear when the scale of galaxies is compared with the scale of separation between them. A galaxy may contain hundreds of billions of stars and span tens of thousands of light years. Even so, the gap to the next major galaxy is often measured in millions of light years. The luminous islands are large, but the dark water between them is vastly larger. When observation widens from one galaxy to many, the crowded appearance fades. The distances begin to dominate the scene. Matter is present, but thinly spread and widely separated. Even inside galaxies, emptiness already plays a strong role. Stars rarely come close to one another. The spaces between them are enormous, but between galaxies the sparseness increases even more. Intergalactic space, meaning the space between galaxies, contains gas so thin that it would seem nearly perfect vacuum by human standards. A vacuum is a region with very little matter in it. On Earth, even the best laboratory vacuum still holds far more particles than the emptiest known cosmic regions. In much of the universe, a cubic meter of space may hold only a few atoms or fewer. Some regions are thinner still. This emptiness is not evenly distributed. Observations show that matter gathers more in some places and less in others. As gravity slowly shapes the universe over billions of years, broad regions with relatively little matter become larger and clearer. These regions are called cosmic voids. A void is not completely empty, but it contains far fewer galaxies than average. Some voids span tens of millions of light years, others extend much farther. Within them, galaxies are sparse. And the thin gas between galaxies is thinner still. If a galaxy drifts within such a region, it may have few near neighbours across immense distances. Voids reveal something essential about scale. A galaxy, even a large one, can feel enormous when described alone. A cluster of galaxies feels larger still. But a void changes the sense of size more deeply, because it is not a thing that can be held in the mind as an object with a bright centre or visible edge. It is a missing abundance spread across a huge volume. The mind is used to thinking in terms of filled space. Cosmic emptiness resists that habit. It asks for attention to absence measured over millions of light years. The darkness of these regions also differs from ordinary darkness on Earth. Night on Earth still contains air, weather, scattered light, and the nearby presence of the ground. Cosmic darkness in the great gaps contains almost none of this familiar setting. There is no broad luminous background except the ancient radiation that instruments detect. There is no sound, because sound needs matter dense enough to carry pressure waves in the ordinary way. There is no horizon made by land or sea. There is only a slow geometry of distance, with a few isolated galaxies and a nearly transparent medium stretching between them. Yet this emptiness is not inactive. Light from distant galaxies travels through it. Gravity crosses it continuously. In many regions, a thin intergalactic gas remains, mostly hydrogen and helium, the simplest and most abundant elements. Hydrogen consists of one proton and usually one electron. Helium contains 2 protons and usually 2 neutrons in its nucleus. This gas is often so diffuse that it does not shine brightly on its own. But it can be detected when it absorbs particular wavelengths of light from more distant sources. In this way, even sparse regions leave traces. They are not invisible because they are non-existent, but because they are so delicate. Dark matter also contributes to the story of emptiness. Although it does not emit light, observations indicate that it provides much of the mass that shapes large cosmic structure. Even where ordinary matter is sparse, dark matter may still form broad underlying distributions. It helps guide where galaxies become more likely and where voids become emptier. The visible emptiness of the universe therefore rests on an unseen framework that influences the motion of matter without revealing itself directly to the eye. The great intervals also affect time as much as sight. Light needs time to cross them, and that time can be measured in millions or billions of years. A signal sent from one galaxy to another often takes longer than the entire span of human civilization by a factor so large that comparison becomes almost meaningless. Even within the observable universe, many regions are forever isolated in practical terms. Nothing travelling at or below the speed of light can easily bridge such distances within any short cosmic age. Scale becomes not only a matter of size but of separation in time. This is why the universe can be full of objects and still feel overwhelmingly empty. The rare places where matter gathers into stars and galaxies shine vividly, but they occupy only a minute fraction of the whole. Images made by telescopes often frame those rare places because that is where light is strongest and detail is richest. The camera naturally favours what glows. The eye follows brightness, but the actual cosmos is governed by proportion, and proportion gives the greater share to nearly vacant space. The emptiness is also part of the reason the universe remains transparent across such enormous distances. If space were crowded everywhere with dense clouds of matter, light would be blocked or scattered much more often. Instead, after leaving its source, light can often travel for immense spans through the dark between galaxies. It is stretched by expansion and bent slightly by gravity. but much of it passes through regions that are nearly clear. The vast empty intervals act not as barriers but as long, quiet passages. In this way, the universe presents a gentle contradiction. It is rich in structure, yet mostly unfilled. It is filled with light, yet mostly dark. It contains matter in quantities beyond ordinary imagination, yet spreads that matter across a volume so immense that emptiness becomes its most common condition. The quiet between the galaxies is not a minor feature surrounding the real contents. It is the main setting in which all visible things are placed. Across the largest scales that can be seen, the universe is first a realm of vast separation, where the rare gatherings of matter float within an ocean of almost nothing. Across the great emptiness, matter does not remain scattered at random. Over immense spans of time, gravity draws it into patterns. These patterns are not simple rows or rings. They form an intricate arrangement of long strands, dense knots, and broad hollow regions. Astronomers call this arrangement the cosmic web. The word web helps because it suggests connection across distance, with thin lines joining larger intersections on the largest visible scales. Galaxies are not spread evenly through space. They gather along filaments, which are long thread-like regions containing galaxies, gas, and dark matter. Between these filaments lie the voids, where far fewer galaxies appear. The result is a universe whose matter resembles a loose network stretched across unimaginable distances. This structure does not arise from late chaos. Its first outline is already present in the tiny variations seen in the ancient background light. In the early universe, some places are only slightly denser than others. These differences are extremely small, yet gravity acts patiently. A denser region pulls a little more strongly on its surroundings. Matter drifts inward. As more matter gathers, gravity grows stronger there, and the process continues. Regions that begin slightly less dense tend to lose material to their denser neighbours. Over billions of years, small unevenness becomes broad form. The web is therefore a slow enlargement of early differences, made visible by time. Dark matter plays a central role in this growth, because it does not interact with light in the ordinary way. It does not shine, scatter, or glow. Yet observations indicate that it contributes most of the matter that shapes large-scale structure. It begins gathering under gravity early, providing a framework into which ordinary matter later falls. Gas follows these deeper gravitational wells, where the dark matter distribution forms ridges and nodes. Ordinary matter becomes more likely to collect. Galaxies then form within those regions. In this picture, the bright parts of the universe do not create the large pattern by themselves. They mark the luminous traces of a much larger invisible arrangement. The filaments of the cosmic web are immense. Some stretch across hundreds of millions of light years. Within them, galaxies are not packed edge to edge, but their numbers are greater than in the emptier spaces nearby. Gas also threads these regions, sometimes heated to very high temperatures as matter flows inward and compresses. This gas can be difficult to detect because it is thin, but it contributes to the mass and motion of the web. At the intersections of filaments, matter gathers more strongly still. These intersections become the sites of especially rich concentrations of galaxies. The web is not built from sharp lines. It has softness and spread. A filament may contain denser spines and looser outer regions. Its edges are not always neatly defined. Gravity shapes matter continuously, rather than drawing exact borders. Even so, when astronomers map the positions of galaxies over very large volumes, the pattern becomes unmistakable. Galaxies trace long connected strands. wide, under-dense regions open between them. The overall form is not imposed by human imagination. It appears repeatedly in surveys and matches what physical models of cosmic growth predict. To see such a structure requires more than a single image. No telescope photograph can simply capture the full web at once. The scale is too large, and the depth extends across billions of light years. Instead, astronomers build maps by measuring the positions and distances of many galaxies. Distance is often estimated from redshift, the stretching of light toward longer wavelengths as space expands. With enough measurements, the three-dimensional distribution begins to emerge. What looks from one angle like scattered points becomes, in a larger reconstruction, a connected architecture. This architecture is one of the clearest signs that the universe has evolved under consistent physical laws over a very long time. Random placement would not produce the same rich pattern of filaments and voids seen again and again. The web reflects the joint action of expansion, gravity, ordinary matter, dark matter, and the early conditions recorded in the background light. Computer simulations that begin with those early conditions often grow into structures that resemble what is observed. This does not mean every detail is known perfectly. It means the broad process is well supported. A smooth young universe with tiny unevenness can, over billions of years, become a web. The cosmic web also changes the meaning of scale. A single galaxy feels vast. A group of galaxies feels vaster. But the web introduces a scale where even galaxies begin to resemble grains laid along giant invisible currents. The human mind is accustomed to measuring by isolated things one mountain, one ocean, one planet. The web asks for another way of seeing. It asks for structure made not only of objects, but of relation between objects over enormous distance. The pattern itself becomes the subject. Size is no longer simply the diameter of one body. It becomes the span of connection across space. Light helps reveal this structure, but gravity shapes it more deeply than light can show. Some regions of the web are marked by luminous galaxies. Other regions hold matter that is much harder to detect directly. The full mass of a filament may exceed what visible stars alone would suggest. In some cases, the presence of hidden mass is inferred by gravitational lensing, a process in which mass bends the path of light. When light from a distant source passes through a region rich in matter, its path curves slightly. By studying these distortions, astronomers can estimate where mass lies, including mass that emits no light. The web is also dynamic. Matter continues to move within it. Galaxies drift along filaments. Gas falls inward. Intersections grow richer over time as surrounding material flows toward them. Expansion stretches the universe overall, yet gravity still gathers matter locally and regionally into more concentrated forms. The result is a tension between spread and collection. Space grows larger, while structure sharpens within it. The web embodies both tendencies at once. It is a pattern formed inside an expanding universe, not in opposition to expansion but through its history. Although the cosmic web is often described in visual terms, its deeper significance lies in what it says about origin and growth. It shows that the universe is neither featureless nor arranged around a central design visible from one privileged place. The same kind of network appears across the observable cosmos. No single filament stands as the main axis of everything. No central knot defines the whole. Instead, structure emerges through local gravity acting on early conditions everywhere. The web is broad, distributed, and without a visible center. In that sense, the cosmic web is one of the clearest answers to the question of how large the universe feels when examined honestly. It is not merely large because it contains many things. It is large because those things are arranged across distances so great that only the largest patterns remain meaningful. Galaxies become markers on strands. Voids become chambers of absence. The web stretches over the dark like a slow record of gravity at work, linking matter across a realm where emptiness still dominates, but no longer reigns alone. Beyond the filaments and voids, matter also gathers into regions so broad that they begin to challenge ordinary habits of naming. Astronomers use the word supercluster for one of these immense regions. A supercluster is a large association of galaxy groups and galaxy clusters spread across tens or hundreds of millions of light years. It is not usually a single compact object with one clear edge. It is a broad zone where matter is more concentrated than average, where many clusters, groups, and filaments lie in related positions and influence one another through gravity. On these scales, the universe appears not only patterned, but organized into vast provinces of matter. A supercluster is larger than a galaxy cluster and less tightly held together. A galaxy cluster is often gravitationally bound, meaning its contents are held in a shared system by gravity strongly enough that they remain associated over long periods. A supercluster is often looser. Some of its parts may move together for a time, while other parts participate more in the general expansion of the universe. For this reason, the word supercluster names a region of enhanced structure rather than a single solid unit. It marks an area where the cosmic web thickens and where many rich systems appear in connected arrangement. These great regions become visible only when astronomical maps cover enormous volumes. A single telescope field cannot easily show their full extent. Their reality emerges from many measured distances and positions brought together into large surveys. When enough galaxies are plotted in 3 dimensions, broad concentrations appear, filaments converge, clusters gather into neighboring chains. The web begins to show regional weight. These are the superclusters, not isolated from the web, but formed as its more crowded domains. One such region includes the supercluster environment around the Milky Way. Modern work describes local large-scale structure in terms of matter flowing along gravitational gradients toward denser basins. In this view, galaxies and clusters do not simply sit in fixed positions within a pattern. They move slowly in response to surrounding mass. A basin of attraction is a region toward which matter tends to drift under gravity. Much as rainwater on land slowly finds its way into a valley. The comparison is not exact, because cosmic matter moves in expanding space and under far subtler conditions, but it helps clarify the idea. Superclusters can often be understood through these broad flows. These motions are called peculiar velocities. The term means motion relative to the average expansion of the universe. A galaxy moves away from distant galaxies because space expands, but it may also have an additional motion caused by nearby gravitational pulls. On small scales, this motion may be a few hundred kilometers per second. Across large regions, many galaxies can share a broad drift toward a more massive area. By measuring these extra motions, astronomers trace the hidden distribution of matter, including dark matter. In this way, flow becomes a map. Motion reveals landscape. The study of large cosmic flows shows that matter does not spread outward in perfect simplicity. Expansion sets the broad background, yet gravity adds texture. Galaxies fall toward denser regions, and filaments guide that movement. Clusters draw in nearby groups. Superclusters become domains in which this slow inward drift is more noticeable. The motion is not hurried. Across human timescales, the sky looks nearly unchanged, but across billions of years, These flows reshape the large-scale arrangement of matter and deepen the contrast between rich regions and sparse ones. This perspective also changes the sense of cosmic size. A supercluster is not only large because it spans a huge distance, it is large because it collects many already vast systems into one broader gravitational setting. A single galaxy cluster may contain hundreds or even thousands of galaxies. A supercluster may contain many such clusters, along with smaller groups and long bridges of matter between them. The mind is asked to step beyond counting galaxies and begin counting landscapes made of clusters. Scale becomes layered. Each level contains structures that are already immense, yet each level also belongs to something larger. Even so, superclusters are not the final containers of everything. They have internal variety. Some regions are denser and more influential. Others are more lightly connected. Their boundaries can be uncertain because the universe does not place bright lines around its structures. Observations indicate where matter is more likely to flow and where connections are stronger. But the edge of a supercluster is often a matter of definition rather than a hard physical border. This uncertainty is not a weakness in the science. It reflects the soft, continuous way gravity shapes large cosmic regions. The motions within these regions are also shaped by matter that cannot be seen directly. Dark matter contributes much of the gravitational field. Without it, the observed motions of galaxies and clusters would not match the visible mass alone. Supercluster flows therefore provide one more indication that the universe contains far more mass than starlight reveals. The bright galaxies serve as markers within a deeper terrain. They trace ridges and valleys of gravity whose full substance remains mostly invisible. Hot gas also occupies some of these broad environments, especially around rich clusters within superclusters. This gas can reach very high temperatures and emit X-rays, a form of energetic light invisible to human eyes but measurable by instruments. The gas does not fill all of supercluster space uniformly, yet it adds to the picture of matter moving, heating, and gathering within large gravitational domains. The universe at this scale is not a silent arrangement of separate islands. It is a slow circulation of matter across an enormous network. Large-scale flow studies have also shown that the Milky Way is not still with respect to the cosmic background. It shares motion with nearby galaxies, and together they participate in broader regional drift. This does not place the Milky Way at any special center. Every large region has its own local motions shaped by nearby mass. What matters is not privilege of position, but the fact that gravity remains effective across astonishing distance. Even on scales of tens or hundreds of millions of light-years, matter responds to matter. The grandeur of a supercluster lies partly in its size and partly in its gentleness. It is not a rigid object. It is a long pattern of association, a broad territory of influence, a gathering of already giant systems moving through expanding space under shared gravitational pull. The motions are real, but they are measured in patient change. Nothing about them resembles the rush of weather or the collapse of a landslide. Their action belongs to cosmic time, where whole clusters drift as quietly as dust in still water. Seen in this way, the universe grows larger not merely by adding more distance, but by revealing new levels of order across that distance. Superclusters show that the web has regions of emphasis, places where matter thickens and where motion gains direction. They present the cosmos as a hierarchy of structure, each level broad enough to humble the last. A galaxy is vast, a cluster is vaster, a supercluster spreads farther still, not as a single bound body, but as a broad current of matter and gravity, carrying entire families of galaxies through the long, measured history of the universe. Within the broad regions of superclusters, some concentrations of matter become more clearly defined. These are galaxy clusters, the largest systems in the universe that are strongly held together by their own gravity. A galaxy cluster is not a simple pile of galaxies gathered by chance. It is a deep gravitational structure in which many galaxies, vast clouds of hot gas, and a much larger amount of dark matter remain associated over immense spans of time. On this scale, matter is no longer merely arranged in a loose regional pattern. It is bound into a shared system with a recognizable center, internal motion, and measurable mass. A rich galaxy cluster may contain hundreds or even thousands of galaxies. These galaxies do not sit quietly like lanterns hung in still air. They move through the cluster at high speeds, often thousands of kilometers per second, each following the pull of the whole mass around it. The cluster remains together not because the galaxies are motionless, but because the shared gravitational field is strong enough to keep them from escaping easily. In this way, a cluster resembles a swarm held in a common well of gravity, though on a scale so large that ordinary comparison soon begins to fail. The visible galaxies are only one part of the cluster. In photographs, they seem to define the object because they shine with starlight. Yet observations show that most of the ordinary matter in many clusters is not locked inside stars. It exists as thin gas spread through the space between galaxies. This gas is heated to enormous temperatures as it falls into the gravitational well of the cluster and is compressed. At such temperatures, it emits X-rays. X-rays are a very energetic form of light, invisible to human sight but detectable with special instruments. In many clusters, this hot gas shines more strongly in X-rays than the galaxies do in visible light. The cluster is therefore not only a gathering of galaxies, it is also a vast atmosphere of extremely hot plasma filling the spaces between them. Plasma is matter in which electrons are no longer bound to atomic nuclei. In the hot gas of a cluster, atoms are broken apart into charged particles. This gas is still very thin by everyday standards, far thinner than any ordinary breath of air. Yet because it fills such an enormous volume, its total mass becomes immense. The gas does not distribute itself perfectly evenly. It often grows denser toward the cluster center, where gravity is strongest. In some clusters, the central gas cools somewhat over time and can influence the evolution of the galaxies near the core. The details vary from cluster to cluster, but the broad picture remains steady. A galaxy cluster is a system of galaxies moving through a huge reservoir of hot, tenuous gas. Deeper still than the gas lies the dominant mass component, dark matter. Observations indicate that the visible galaxies and hot gas together account for only part of the total gravitational pull. The rest appears to come from matter that does not emit or reflect light in the ordinary way. Dark matter creates most of the cluster's gravitational well. It provides the hidden structure that holds the whole system together. This conclusion does not rest on a single line of evidence. It comes from the motions of galaxies, the temperature of the gas, and the bending of light by gravity. Each method points toward the same broad result. A galaxy cluster contains much more mass than can be seen directly. One of the clearest signs of this hidden mass comes from gravitational lensing. A lens bends light. In ordinary optics, glass bends light because it changes the speed at which light travels through it. In gravity, mass bends the path of light by curving the geometry through which light moves. When a massive cluster lies between Earth and a more distant galaxy, the background light can be distorted, stretched, or multiplied. Astronomers study these distortions to map the cluster's total mass. In many cases, the mass traced by lensing extends well beyond the bright galaxies and hot gas alone. The cluster reveals itself as a deep invisible structure outlined by the way it deflects light. The galaxies within a cluster also differ from galaxies in quieter environments. Close passages, tidal forces, and repeated encounters can gradually alter them. Tidal force means the difference in gravity across an object, which can stretch or disturb it. In a dense cluster, galaxies pass one another more often than in sparse regions. They may lose gas, change shape, or reduce the rate at which new stars form. The cluster environment is therefore not just a container. It is a setting that influences the life of the galaxies inside it. Over time, a crowded cluster can become home to many older, redder galaxies with less active star formation than those in less dense surroundings. At the center of some clusters, one especially large galaxy dominates. This central galaxy may grow by merging with others over long periods. It can become enormous, extending far beyond the size of a typical spiral galaxy. Around it, the cluster core often shows the strongest concentration of galaxies and the densest hot gas. Yet even here, the central region is not a quiet heart in the ordinary sense. Galaxies continue to move, gas continues to stir, heat, and sometimes cool. Dark matter continues to shape the deeper gravitational frame. A cluster is stable in the broad sense, but alive with motion inside. The size of a galaxy cluster is difficult to absorb because each component is already immense. The galaxies are large. The gaps between them are larger. The hot gas fills a region millions of light-years across. The dark matter halo, meaning the broad distribution of dark matter surrounding the visible system, extends farther still. A person looking at a cluster through a telescope may see only a crowded patch of faint galaxies, but the true object is far more substantial than the eye alone suggests. It is a massive three-part system of stars, plasma, and unseen matter, bound together across a volume so large that light itself needs millions of years to cross it. Galaxy clusters also serve as markers of cosmic history. Their abundance, mass, and distribution help astronomers test how structure grows in the universe. Observations indicate that clusters form over time as smaller groups merge, and matter falls inward along filaments of the cosmic web. In that sense, a cluster is both a present object and a record of long gravitational assembly. It carries within its structure the history of earlier growth. The rich systems seen today are not sudden creations. They are the outcome of billions of years of gathering. Some clusters continue to collide and merge with one another. When this happens, galaxies may pass largely unharmed because the distances between stars are so vast, but the hot gas can crash together, compress, and heat further. Dark matter distributions may move through one another more freely. Such events provide valuable tests of cluster physics and of the behavior of dark matter. Even in collision, the immense scale of the system remains central. Whole clusters can interact over periods that exceed the rise and fall of all human civilizations by many orders of magnitude. A galaxy cluster therefore stands as one of the clearest examples of bound immensity. It is larger than any single galaxy by far, yet more coherent than a supercluster. It gathers many separate realms of stars into one deeper gravitational system. It contains visible matter in several forms and far more hidden mass than light alone can show. In the slow architecture of the universe, it is a great knot in the cosmic web, dense, hot, and heavy, holding hundreds or thousands of galaxies within one enormous field of gravity. The local group is a small gathering of galaxies held together by gravity within a much larger universe. Small is only a relative word here. The region spans roughly 10 million light-years from side to side, a distance so large that light, moving at its full speed, would need 10 million years to cross it. yet against the scale of clusters and superclusters. This remains a modest family. It contains more than 50 known galaxies, and probably more faint dwarf galaxies remain to be identified. Most of these are small and dim. A few dominate the whole system. The Milky Way and the Andromeda Galaxy are the two great members. The Triangulum Galaxy follows as a smaller but still substantial spiral. Around them gather many dwarf galaxies, scattered like faint companions through the shared gravitational field. A galaxy group is smaller than a galaxy cluster and far less crowded. The local group does not contain hundreds of large galaxies packed into a dense common atmosphere of hot gas. Its members are more widely spaced, and the system is quieter. Even so, gravity binds it. The galaxies do not simply drift apart with the general expansion of the universe. Their mutual attraction is strong enough to overcome expansion within this region. That is one of the defining features of a gravitationally bound system. On very large scales, space expands and distant galaxies recede. Within the local group, local gravity governs the motion more strongly. The Milky Way and Andromeda account for most of the visible mass in stars. Each is a large spiral galaxy with hundreds of billions of stars. Around both lie swarms of smaller companions. These dwarf galaxies are faint because they contain far fewer stars. Some are irregular in shape, with loose and uneven structure. Others are dwarf spheroidal galaxies, meaning they're small, rounded, and diffuse, with little gas and no clear spiral arms. Many of these dwarfs orbit one of the two giant spirals, though some move more independently within the larger group. The local group is therefore not arranged like a tidy ring or a balanced geometric figure. It is more like a pair of major gravitational centers with a number of lesser members distributed around them. The Milky Way and Andromeda each possess their own retinues, yet both also belong to the wider group. Between them lies a long interval of intergalactic space. The present distance between the two great spirals is about 2.5 million light-years. This is close enough, in cosmic terms, for their gravity to matter strongly to one another, yet far enough that each remains a separate galaxy with its own structure and satellites. The motion of Andromeda with respect to the Milky Way has been studied for many years. Observations indicate that Andromeda is moving toward the Milky Way, not away from it. This inward motion is one of the clearest signs that the local group is a true bound system rather than a chance association. The approach is slow on human timescales, but real. It unfolds across billions of years. The two galaxies are not rushing together through empty space in any sudden way. They're following the quiet long-term pull of gravity within the group. That shared pull depends not only on visible stars and gas, but on dark matter. The local group, like individual galaxies and larger clusters, appears to sit within a much larger mass of unseen matter than visible light alone reveals. Each giant spiral has its own dark matter halo, a broad distribution of dark matter surrounding the luminous galaxy. These halos extend far beyond the bright disks, within the local group. The halos of the major galaxies influence the motions of dwarf companions and the overall dynamics of the system. When astronomers estimate the mass needed to explain the observed motions, visible matter by itself is not enough. Dark matter again provides the deeper gravitational framework. One traditional way to estimate the mass of the local group is called the timing argument. The basic idea is simple. If the Milky Way and Andromeda begin farther apart in the expanding early universe and later slow, stop separating, and begin to approach because of mutual gravity, then their current distance and speed contain information about the total mass involved. The exact calculation depends on assumptions and modern refinements, but the central lesson remains clear. The two galaxies require far more mass than stars and gas alone can provide. Their slow approach speaks of a heavy invisible component surrounding them. The dwarf galaxies add further detail to this family picture. Some orbit close to the Milky Way, such as the Large Magellanic Cloud and the Small Magellanic Cloud, which are among the most prominent nearby companions. These are irregular dwarf galaxies containing gas and active star formation. Others are fainter and more diffuse, with old stars and little remaining gas. Around Andromeda, many dwarf companions have also been identified. Some seem arranged in broad planes, thin, flattened groupings that remain an area of active study. Observations indicate the pattern is real, though its full significance and long-term stability remain uncertain. The local group is therefore not only a quiet family, but also a place where some details still resist complete explanation. There is also a thin medium between the galaxies, a sparse intergalactic gas that is difficult to observe directly. It does not dominate the appearance of the group, but it contributes to the environment through which galaxies move. The local group is not empty between its members, though it is extremely diffuse. Light crosses these distances almost undisturbed. The region is mostly dark, lightly seeded with matter, and shaped primarily by the gravity of its largest members. The local group matters because it is the immediate galactic neighborhood of the Milky Way. It provides the nearest example of how galaxies live in company rather than isolation. A galaxy is not always alone in the cosmic web. It may belong to a group, sharing motion, origin, and future interaction with nearby companions. In the local group, this truth becomes easier to measure because the members are comparatively near. Individual stars can be studied in some dwarf galaxies. The structure of companions can be mapped in greater detail. Motions can be tracked with better precision than for more distant systems. Yet closeness does not make the scale ordinary. Even within this local family, distances remain immense. The space between the Milky Way and Andromeda is far greater than the full diameter of either bright galactic disk. The dwarf galaxies are separated by hundreds of thousands or millions of light years. The group is local only by comparison with the larger universe. By any human measure, it is vast beyond direct experience. Still, within the architecture of the cosmos, the local group feels like a narrowing of scale and a deepening of familiarity. The great web of matter, the superclusters, and the massive clusters give way here to a quieter unit, a small gravitational household made of a few major galaxies and many faint attendants. It is a region where individual members can be named and their relations traced, where the universe begins to seem less like a distant pattern and more like a neighborhood of separate island systems, all held together in one wide and patient field of gravity. The Milky Way is the large spiral galaxy in which Earth and the solar system reside. From outside, it would appear as a broad disk of stars and dust with curved spiral arms winding outward from a bright central region. From inside, its shape is harder to see directly. No observer within it can rise above the disk and look down upon the whole. The galaxy must instead be understood by combining many observations: the positions of stars, the motion of gas, the glow of dust, the radio signals of hydrogen, and the measured distances to many different objects. From these separate strands, a picture emerges of a vast stellar system stretching across roughly 100,000 light-years. Though exact values remain somewhat uncertain because measuring the full structure from within is difficult. The Milky Way is called a barred spiral galaxy. A bar is an elongated central structure made of stars crossing the inner region. Spiral arms extend outward from the ends of this bar and from nearby inner zones. These arms are not rigid solid lanes. They are regions where stars, gas, and dust are somewhat more concentrated than average. They move through the disk as patterns rather than as fixed objects. A spiral arm can be understood as a traffic wave in a crowded road. The cars move in and out of the dense region, but the pattern of higher density continues. In the galaxy, stars and gas orbit the center, yet the spiral form remains as a long-lived structure shaped by gravity and motion. The disk of the Milky Way contains most of its visible stars. It is broad and thin in proportion to its width, with a central bulge rising in the middle and spiral structure spread through the outer regions. If the galaxy were reduced to the size of a large plate, the thickness of its main stellar disk would be only a small fraction of that width. Even so, the thickness is still measured in hundreds or thousands of light years, and the stars within it occupy enormous separations from one another. The disk seems full only because so many stars lie along the line of sight. In truth, the space between stars remains immense, even in the richer parts of the galaxy. Seen from Earth on a dark night, the Milky Way appears as a pale band arcing across the sky. This light comes from countless unresolved stars in the galactic disk. The band looks bright where the line of sight passes through denser regions of the disk and the central parts beyond. It looks darker where thick dust clouds block the light behind them. These dark lanes are not empty cuts in the galaxy. They are concentrations of interstellar dust, meaning tiny solid particles mixed with gas between the stars. Dust grains are often made from carbon-rich or silicate material, and though individually minute, together they can obscure vast regions of starlight. The gas and dust of the Milky Way are crucial to its structure. The interstellar medium, the material between stars, is not a uniform mist. It forms clouds of different densities and temperatures. Some clouds are cold and dense enough for gravity to gather them into regions where new stars form. Others are thin and hot, stirred by stellar winds and explosions from dying stars. The spiral arms are especially rich in gas and dust, which is one reason they are associated with young stars. Massive young stars shine brightly and live briefly, so where they're seen in large numbers, recent star formation is usually nearby. This gives many spiral arms a blue-white brilliance when viewed in other galaxies. The Milky Way does not present all its structure equally well to visible light. Dust blocks much of the view toward the inner galaxy. For that reason, astronomers use other parts of the spectrum to map it. Radio observations of neutral hydrogen are especially important. Neutral hydrogen, ordinary hydrogen with its electron attached, emits radiation at a characteristic wavelength in the radio range. This signal can pass through dust and helps trace the distribution and motion of gas across the galaxy. Carbon monoxide is also used as a marker for denser molecular clouds, where hydrogen often exists in molecular form but is harder to detect directly. By using these signals, astronomers reconstruct the spiral structure more clearly than visible light alone allows. The galaxy rotates, but not as a solid wheel. Stars closer to the center complete an orbit more quickly than those farther out, though the pattern is influenced by the total mass distribution of the galaxy. The Sun, located well out in the disk, takes about 230 million years to complete one orbit around the galactic center. This period is sometimes called a cosmic year. It means that during the whole history of complex life on Earth, the solar system has completed only a modest number of circuits around the galaxy. The sense of motion is real, but it belongs to timescales far longer than ordinary imagination handles easily. Within the disk, stellar populations vary. Some stars are young, hot, and bright, often found near the spiral arms and the gas-rich regions where they form. Others are older and more settled into broader orbits. open clusters, which are loose groups of stars born from the same cloud, are common in the disk. So are nebulae, clouds of gas and dust that may either form stars or glow under the radiation of nearby young stars. Supernova remnants also mark places where massive stars have ended their lives in powerful explosions, returning heavy elements to the interstellar medium. The disk is therefore not merely a flat arrangement of stars, it is a living cycle of birth, radiation, motion, and death repeated across a huge rotating structure. The central region of the Milky Way appears brighter and thicker because stars are more concentrated there. Even from within the disk, the direction toward the center is marked by a richer and denser field of stars. Yet the details are partly hidden by dust, which makes the inner galaxy a place best studied with infrared and radio observations. Infrared light has longer wavelengths than visible light and can pass more easily through dusty regions. This allows astronomers to detect stars and structures that would otherwise remain concealed. Through such studies, the central bar and the thicker inner bulge become clearer parts of the galactic picture. Despite all this complexity, the Milky Way is not unusual in the broad cosmic sense. It is a large spiral galaxy of a common major type, neither the largest known nor among the smallest. That ordinary status is important. The home galaxy is impressive, but not singular. Its size, structure, and content make it a representative example of a major star-forming spiral in the present universe. This ordinary nature helps astronomers use it as both a home environment and a standard of comparison. By studying other spirals, they better understand the Milky Way. By studying the Milky Way in detail, they better understand spirals elsewhere. The disk of the Milky Way is therefore a great layered field of stars, gas, dust, and motion, broad enough that light needs 100,000 years to travel from one side to the other. It is the bright main body of the galaxy, the region that gives the Milky Way its familiar band across the sky and most of its visible mass in stars. Inside it, the solar system is only one small participant among hundreds of billions. Yet even this immense stellar disk is not the whole of the galaxy. Around and beyond its bright visible structure, fainter and more extended components continue outward into a region where stars thin, clusters linger, and the unseen weight of dark matter becomes still more important. Beyond the bright disk of the Milky Way, the galaxy does not end at a sharp rim. Its visible starlight fades, the dust lanes thin, and the familiar spiral structure loses its hold. But the galaxy continues into a much broader and fainter region called the halo. A halo is an extended outer component surrounding the main body of a galaxy. In the Milky Way, this halo contains a sparse population of stars, ancient globular clusters, thin streams of disrupted satellites, and a far larger distribution of dark matter that reaches well beyond what light can directly show. If the disk is the luminous body of the galaxy, the halo is its long, quiet outer presence, difficult to see in one view, yet essential to the galaxy's true size. The stellar halo is extremely thin compared with the disk. Its stars are spread across a huge volume, and in most directions they are so sparse that the sky does not glow with them in any obvious way. These stars are often old and poor in heavy elements. Heavy elements, in astronomy, means all elements heavier than hydrogen and helium. Such elements are made inside stars and spread by stellar winds and explosions. A star with few heavy elements usually forms early in cosmic history, before many generations of stars have had time to enrich the surrounding gas. For that reason, the halo preserves a record of the Milky Way's early growth. Its stars are not just far out, many of them are also ancient. The shape of the stellar halo is not a thin plane like the disk. It is much rounder and more extended, reaching above and below the galactic plane in all directions. This different geometry reflects a different history. The disk forms from gas settling into a rotating flattened structure. The halo forms more through the accumulation of smaller systems, chaotic early motions, and long gravitational mixing. Some halo stars may form in the early Milky Way itself. Others appear to come from smaller galaxies that fall inward and are gradually torn apart by the galaxy's gravity. Over long ages, their stars spread into the halo, leaving behind faint streams that still trace the path of the original intruder. These stellar streams are among the clearest signs that the Milky Way grows by absorbing smaller galaxies. A dwarf galaxy entering the Milky Way's gravitational field does not always remain intact. The pull on its near side and far side is not quite the same. This difference, called tidal force, can stretch the smaller system and strip stars from it. Those stars continue orbiting the Milky Way in long ribbons. Some streams remain coherent enough to identify as shared structures across the sky. Others disperse more fully and merge into the general background of the halo. In either case, they show that the halo is not a smooth static shell. It is an archive of past mergers written in the motions and positions of stars. Among the most striking members of the halo are the globular clusters. A globular cluster is a dense, roughly spherical collection of stars held together by its own gravity. The Milky Way contains around 150 known globular clusters, with a few more possible candidates still under study. Each cluster may hold tens of thousands to millions of stars packed into a relatively compact region. These clusters are old, often among the oldest visible stellar systems in the galaxy. Their stars usually share low heavy element content, though not all clusters are chemically simple. Because of their age and distribution, globular clusters help trace the halo and the early history of the Milky Way. A globular cluster differs greatly from the loose open clusters found mainly in the disk. Open clusters are younger, more irregular, and more easily disrupted. Globular clusters are tighter, older, and more durable. They orbit far above and below the galactic plane, often on elongated paths that carry them through the halo, in a dark sky. If human eyes were close enough to one, it would appear as an intense swarm of stars concentrated toward the center, from Earth. Even the nearest globular clusters appear as compact luminous knots through small instruments, while larger telescopes resolve them into dense fields of individual stars. The halo also contains very little cold gas compared with the disk. Star formation is therefore far less active there. The outer galaxy is not a region of rich spiral nurseries or thick dust clouds glowing under newborn stars. It is more austere. Its visible contents are old stars, sparse streams, and ancient clusters moving through broad dark space. Some hot gas exists in the wider circumgalactic medium, a very extended and thin gaseous envelope surrounding the galaxy. But this gas is difficult to observe directly. It contributes to the environment of the halo without giving it the bright texture seen in the disk. The circumgalactic medium matters because the galaxy does not live in a perfect vacuum beyond its stars. Thin gas surrounds it, reaches outward, and interacts with inflowing material, galactic winds, and satellite systems. This gas may serve as a reservoir that gradually feeds star formation in the disk over long time periods. It may also receive material driven outward by supernova explosions and activity near the galactic center. Observations indicate that this medium is extensive and complex, with different temperatures and densities in different regions. Yet even taken together, its density remains extremely low by everyday standards. The halo remains, in visible terms, a place of sparse matter. Deeper than all these visible or detectable baryonic components lies the dark matter halo. Baryonic matter means the ordinary matter made of protons and neutrons, the matter that forms stars, gas, dust, planets, and people. The dark matter halo is far more massive than the visible galaxy. It extends far beyond the bright disk and stellar halo, surrounding the Milky Way in a huge invisible envelope. Astronomers infer its presence from the motions of stars and gas, especially in the outer galaxy, where visible matter alone cannot explain observed orbital speeds. If the galaxy's mass were only what shines, stars far from the centre would orbit more slowly than they do. Instead, the outer rotation remains too fast for visible matter alone. The conclusion is that a much larger unseen mass surrounds the galaxy. This dark halo strongly affects the Milky Way's true scale. The bright disk spans about 100,000 light-years, but the dark matter halo may reach several 100,000 light-years, possibly more depending on how one defines its outer extent. The exact boundary is uncertain because dark matter does not present a visible edge. Its density gradually declines with distance rather than ending sharply. Even so, the key fact is clear. The galaxy is much larger than its visible starlight suggests. The familiar river of stars seen in the night sky marks only the inner, brighter part of a far broader gravitational system. The halo also forms the environment through which the Milky Way's satellite galaxies move. The Large Magellanic Cloud, the Small Magellanic Cloud, and many dwarf spheroidal companions orbit within this wider field. Their motions help astronomers estimate the mass and extent of the dark halo. As these satellites move, some are gradually stripped of stars or gas, contributing new material to the halo. The process continues the slow growth of the galaxy through accretion, the gradual addition of smaller bodies. In this region, the Milky Way becomes harder to picture because the eye is no longer guided by a bright band or clear spiral arms. The halo asks for another kind of imagination, one shaped by absence, sparsity, and hidden mass. It is the outer galaxy not as a shining wheel, but as a vast sphere of faint remnants and invisible gravity. Here the visible stars grow rare, ancient clusters drift in long orbits, and dark matter sets the deeper limits of the galactic domain. The home galaxy, already immense in its bright disk, becomes larger still when its quiet outskirts are understood. Within the broad disk of the Milky Way, the solar system lies in a smaller neighbourhood often called the Orion Arm, or more precisely the Orion Spur. A spur is a lesser branch of galactic structure, smaller than the major spiral arms but still part of the larger pattern of stars, gas, and dust in the disk. This region is not near the galactic centre, and it is not close to the far outer edge either. It lies in an intermediate zone, several tens of thousands of light-years from the centre of the Milky Way, where the density of stars is moderate and the structure of the galaxy is easier to inhabit than to view. Here, on a local scale still far beyond any ordinary measure, the universe narrows from the full breadth of the galaxy to the district of stars surrounding the Sun. The Orion Spur sits between two larger spiral features, the Sagittarius arm inward toward the galactic centre and the Perseus arm farther outward. It is not a simple detached fragment. It is a connected part of the galactic disk, shaped by the same rotation, density patterns, gas clouds, and star formation that influence the Milky Way as a whole. Yet it has a more local identity because it contains the Sun and many of the stars most familiar to astronomy. In maps of nearby space, it appears as a modest stream of stellar and gaseous structure extending through a portion of the disk. one thread among many in the galaxy's broad woven form. The stars in this region are separated by vast distances, yet on galactic terms they form a local neighbourhood. The nearest star system beyond the Sun, Alpha Centauri, lies a little more than 4 light-years away. Many other nearby stars lie within a few dozen light-years. This sounds close only because the rest of the galaxy is so much larger. Even the nearest stars are separated from the Sun by distances so great that any human journey to them remains far beyond present practical reach. Light itself takes years to cross these gaps. The local stellar neighbourhood is therefore local in relation to the galaxy, not in relation to daily experience. Most nearby stars are small and dim. Red dwarfs, which are cool, low-mass stars, make up a large fraction of the stellar population in the region around the Sun. They shine much less brightly than larger stars and can remain stable for extremely long times. Brighter stars, though more striking in the sky, are less common. The local neighbourhood includes a mixture of stellar ages and types-old stars that have orbited the galaxy many times, younger stars born from more recent clouds of gas, binary systems where 2 stars orbit one another, and occasional stellar remnants such as white dwarfs and neutron stars. The region is not exceptional in this variety. It is typical of a broad middle zone in the disk. Among the most important features of the Orion Spur are its clouds of gas and dust. These clouds form part of the interstellar medium and provide the raw material from which new stars can form. Some are diffuse and faint, others are dense molecular clouds, where atoms join into molecules and the gas grows cold enough for gravity to gather it more effectively. Molecular means that atoms are bound together into small groups, such as molecular hydrogen, though that substance is often traced indirectly by other molecules like carbon monoxide. Within such clouds, parts may collapse and fragment, forming protostars, which are young stars still gathering material from their surroundings. The local arm therefore contains both older settled stars and the cold, dark nurseries of future stars. Several well-known star-forming regions belong to this neighbourhood. The Orion Molecular Cloud Complex is one of the most prominent. It lies hundreds of light-years from the Sun and contains a rich arrangement of glowing nebulae, dark dust lanes, and young stars. A nebula is a cloud of gas and dust in space. In Orion, intense radiation from hot young stars causes some of the gas to glow, while surrounding dust blocks light and shapes the view into bright and dark patterns. The region offers a nearby example of how stars form in groups within giant clouds. It is not representative of the whole Orion Spur in every detail, but it shows the kind of active process still present within this local galactic district. The Sun also lies inside a smaller feature called the local bubble, a cavity in the interstellar medium where the gas density is lower than in surrounding regions. This cavity appears to have been shaped by ancient supernova explosions, the deaths of massive stars that release enormous energy and drive shock waves into surrounding gas. Over time, such explosions can sweep material outward and leave behind a region of thinner, hotter gas. The local bubble does not empty space entirely, but it alters the immediate interstellar environment around the Sun. Nearby clouds lie along or beyond its boundaries, and its existence shows that the local galactic neighbourhood is shaped not only by slow rotation and steady star formation, but also by the long aftermath of stellar death. Open clusters and stellar associations are also common in this part of the galaxy. An open cluster is a loose group of stars born from the same cloud and still moving through space together, at least for a time. A stellar association is even looser, a group of young stars sharing a common origin but not always remaining strongly bound by gravity. Such groups gradually disperse as they orbit the galaxy, adding their stars to the wider disk population. Their presence in the Orion Spur shows that starbirth is not evenly scattered one star at a time. It often occurs in clusters and complexes, leaving families of stars that drift apart slowly over millions of years. The local region also contains dust that shapes what can and cannot be seen. Some directions through the galactic plane are relatively clear, revealing large numbers of distant stars. Other directions are obscured by dark clouds. This patchiness affects the way the Milky Way appears from Earth and influences how astronomers map nearby structure. Infrared and radio observations help penetrate the dust, but even then the local neighborhood remains a layered place where stars, clouds, and cavities overlap along the line of sight. The Orion Spur is not a neat lane through empty space. It is a textured environment with varying densities, old stars crossing through young regions, and gas responding to the broad motion of the galactic disk. The Sun's motion through this neighborhood is steady and unremarkable by galactic standards. It orbits the center of the Milky Way along with nearby stars, while also carrying smaller motions relative to them. Over long periods, stars in the local region slowly change their arrangement. Constellations, which seem fixed across human lifetimes, gradually distort across tens of thousands of years as individual stars move along their own paths. The local galactic neighborhood is therefore not a static scene. It is a moving field, quiet in the short term yet constantly changing on larger scales. What makes the Orion Spur important is not grandeur alone, but context. It is the part of the galaxy where the solar system resides, a moderate region in a moderate galaxy, neither central nor remote. Here the scale of the Milky Way becomes more intimate without becoming small. Distances fall from tens of thousands of light years to dozens, hundreds, and thousands, yet they remain immense. The Sun occupies one ordinary position among many stars, embedded in a spur of the galactic disk shaped by gas clouds, stellar birth, ancient explosions, and the long turning of the Milky Way. At the edge of the Sun's immediate dominion, the solar system becomes difficult to picture because its familiar bright members fall away. The large planets are no longer the main landmarks. Sunlight grows weak, temperatures remain extremely low, and the distances between objects become so great that even the broad architecture of the planetary system begins to dissolve into sparse outer territory. Yet the solar system does not end when the last major planet is passed. It continues through a frontier region of icy bodies, scattered objects, and thinning solar influence that stretches far beyond the orbit of Neptune. This outer realm is the frontier of the Sun's household, where the inner order of planets gives way to a much wider and quieter domain. Just beyond Neptune lies the Kuiper Belt, a broad ring-like region containing many icy bodies left over from the formation of the solar system. These objects are made largely of frozen water, methane, ammonia, and other volatile substances, mixed with rock. Volatile here means a substance that easily evaporates or escapes as gas under warmer conditions. In the deep cold beyond Neptune, such materials remain solid. The Kuiper Belt is not a dense swarm with bodies packed closely together. It is spacious and thinly populated across an enormous volume. Even where many objects exist, the intervals between them remain immense. The region only appears crowded in diagrams because human images compress scale in order to show structure at all. Pluto is one of the best-known bodies in this outer belt. Though it is only one member of a much larger population, its orbit is elongated and tilted compared with the major planets, and many similar objects share related traits. Some are smaller, some comparable in size, and a few approach Pluto in significance as dwarf planets. A dwarf planet is a body massive enough for its gravity to pull it into a roughly round shape. but not dominant enough to clear its orbital neighborhood of other objects. This definition reflects the outer solar system well, where many bodies remain in overlapping gravitational relations rather than forming one simple sequence of isolated rulers. The Kuiper belt extends outward for many billions of kilometers. Within it, some objects move in stable resonances with Neptune. A resonance means that orbital periods fall into simple numerical relationships. Pluto, for example, completes 2 orbits round the Sun for every 3 of Neptune. This shared timing prevents close encounters and preserves long-term stability. Other objects occupy different dynamical classes, meaning categories defined by their orbital behavior. Some remain in relatively calm circular paths. Others follow more inclined or stretched orbits, shaped by the history of planetary migration early in solar system formation. Beyond the main Kuiper belt lies an even more scattered population. These are the scattered disk objects, bodies that appear to have been thrown onto distant elongated paths by gravitational interactions, especially with Neptune in the ancient past. Their orbits can carry them far from the Sun and then bring them back inward again over immense timescales. In this region, the solar system becomes less like a layered set of rings and more like a cloud of long, patient trajectories, each orbit tracing a private path through deep, cold and faint light. The Sun still governs these objects, but its presence feels remote. At such distances, sunlight is so weak that the Sun would appear only as an intensely bright star rather than a warming disk. These icy frontier bodies matter because they preserve early solar system material. Near the Sun, heat and repeated geological change alter many surfaces and substances. In the far outer system, change is slower and colder. Some objects remain close to the conditions they have held for billions of years. They're not unchanged in every detail, but they serve as time capsules more effectively than warmer worlds do. By studying them, astronomers and planetary scientists gain clues about the disk of gas and dust from which the Sun and planets form. The outer frontier is therefore not only distant, it is ancient in a special way, holding matter that changes very slowly. Farther outward still lies a boundary not marked by solid bodies but by the solar wind. The solar wind is a steady flow of charged particles released by the Sun. These particles stream outward in all directions and carry with them part of the Sun's magnetic influence. For a long distance, this outflow shapes a protective bubble in space called the heliosphere. A sphere is only an approximation here. The true form is influenced by the surrounding interstellar medium and may be somewhat elongated or distorted. Even so, the heliosphere can be understood as the region where the outward pressure of the solar wind dominates over the incoming pressure of the interstellar environment. As the solar wind travels outward, it eventually slows from supersonic to slower speeds in a region called the termination shock. Beyond that lies the heliosheath, where the slowed solar wind continues to press outward against interstellar matter. Farther still lies the heliopause, the boundary where the outward influence of the solar wind is balanced by the pressure of the interstellar medium beyond. This is often treated as the practical edge of the heliosphere. It is not the end of the Sun's gravity, which extends much farther, but it marks the place where the Sun ceases to dominate the local particle environment. Spacecraft have crossed this frontier. Voyager 1 and Voyager 2, launched in the 20th century, travel outward long enough to pass beyond the heliopause into interstellar space. Their journeys reveal that the solar system's outer boundary is not merely theoretical. It can be measured through changes in particle populations, magnetic conditions, and plasma environment. Even so, interstellar space here does not mean the craft have left the Sun's gravitational reach entirely. It means they have entered the region where the interstellar medium, rather than the solar wind, defines the local surroundings more strongly. Beyond the heliosphere, the question of the solar system's extent becomes more subtle. Gravity from the Sun likely controls distant icy bodies in the hypothetical Oort cloud, a vast spherical reservoir thought to surround the solar system at distances far greater than the Kuiper belt. Observations strongly support the existence of such a cloud through the behavior of long-period comets, but it remains uncertain in direct detail because no individual Oort cloud object has yet been confirmed as a clearly observed member at those extreme distances. If it exists as expected, it may extend tens of thousands of astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun. At that scale, the solar system becomes almost a small stellar environment in its own right, fading gradually into the broader galaxy. The frontier of the solar system is therefore not one border but several. There is the outer limit of the major planets, the broad belt of icy remnants, the scattered paths of distant bodies, the heliosphere shaped by the solar wind, and the far possible cloud of cometary reservoirs held by gravity. Each boundary answers a slightly different question. Where do the bright familiar worlds end? Where do icy relics continue? Where does the solar wind yield to interstellar space? Where does the Sun's gravity finally become too weak to hold its most distant companions? None of these limits is a wall. Each is a thinning of influence across distance. In this frontier region, size takes on another meaning. The solar system is no longer merely the space containing planets. It becomes a much wider domain of fading sunlight, rare icy bodies, and invisible fields, extending so far that the gap from the Sun to its outer reaches begins to resemble, in miniature, the larger emptiness of the galaxy itself. The ordered family of worlds remains inside, but here at the edge the Sun's realm stretches outward into cold and sparse immensity, broad enough to remind the mind that even home has an outer darkness. Inside the broad frontier of icy remnants and fading solar wind, the solar system takes on a more familiar structure. Here the Sun gathers the main planetary region into a flattened arrangement of worlds, moons, asteroids, comets, dust, magnetic fields, and moving light. This region is still vast beyond ordinary human sense, yet compared with the far outer frontier, it feels more ordered and more legible. The planets follow paths around the Sun in nearly the same plane because they form from a rotating disk of gas and dust. That early disk leaves its imprint on the mature system. The result is not a random scattering of worlds, but a coherent family shaped by shared origin and long gravitational adjustment. At the center stands the Sun, containing almost all the mass of the solar system. It is a star, a self-luminous sphere of hot plasma powered by nuclear fusion in its core. Fusion is the process by which light atomic nuclei combine into heavier nuclei and release energy. In the Sun, hydrogen gradually becomes helium under tremendous pressure and temperature. The energy produced in the core moves outward and eventually leaves as light and heat. That steady output governs nearly every visible process in the planetary region. It warms planets, drives atmospheres, shapes comet tails, and provides the energy that life on Earth later uses. The solar system is therefore not just a set of orbiting bodies, it is a radiative environment centered on one star. Closest to the Sun lie the terrestrial planets, the smaller rocky worlds of the inner system. Mercury circles nearest, moving quickly through intense sunlight and strong solar gravity. Venus follows, wrapped in a dense atmosphere that traps heat so effectively that its surface becomes hotter than Mercury's despite being farther from the Sun. Earth orbits at a distance where liquid water can persist on the surface under suitable atmospheric conditions. Mars lies beyond, colder and drier, with evidence that liquid water once moved across its surface long ago. These 4 inner planets are made mainly of rock and metal. They're relatively small in radius compared with the giant planets, and their higher densities reflect the concentration of heavier materials in their composition. Between Mars and Jupiter lies the asteroid belt, a broad region containing many rocky and metallic bodies. It is often imagined as a crowded hazard field, but in reality the objects are separated by large distances. The belt remains sparse, though it contains a great many bodies ranging from dust grains to dwarf planets such as Ceres. Ceres is large enough to become roughly spherical under its own gravity, making it a dwarf planet rather than a simple irregular asteroid. The asteroid belt may be understood as leftover building material from the early solar system, material that never gathers into a full planet because the strong gravitational influence of Jupiter stirs the region and prevents easy accumulation. Beyond the belt, the giant planets dominate the middle reaches of the planetary system. Jupiter is the largest planet, a gas giant composed mainly of hydrogen and helium. It has no solid surface in the ordinary sense, but rather a deep atmosphere that gradually thickens into denser interior layers. Saturn, also a gas giant, is smaller than Jupiter, but still immense, and it is surrounded by a spectacular ring system made mostly of ice particles with some rocky material mixed in. Uranus and Neptune, farther out, are often called ice giants because although they also contain hydrogen and helium, they have a larger proportion of heavier volatile substances such as water, ammonia, and methane in their deep interiors. These outer planets possess broad atmospheres, many moons, ring systems of their own, and magnetic fields of varying complexity. The giant planets reshape the whole planetary region through gravity. Jupiter especially acts as a powerful gravitational architect. Its mass affects asteroid orbits, influences comet paths, and contributes to the long-term stability or instability of smaller bodies throughout the system. Saturn, Uranus, and Neptune also shape the wider architecture, particularly in the outer system, where their migration early in solar system history likely alters the distribution of many small bodies. The planetary region is therefore not static. Even when the major orbits remain stable over long periods, countless smaller objects respond to resonances, perturbations, and slow exchanges of angular momentum. Angular momentum is the quantity that describes rotational and orbital motion in a conserved system. It helps determine how bodies move and how orbits shift through time. Moons add another layer of richness to this region. Earth has one large moon relative to its own size. Mars has 2 small irregular moons. The giant planets each possess many moons, some tiny and captured, others large and geologically complex. Jupiter's moon, Europa, likely hides a global ocean beneath an icy crust. Ganymede, another Jovian moon, is larger than the planet Mercury. Saturn's moon, Titan, carries a thick atmosphere and lakes of liquid methane and ethane on its surface. Enceladus releases plumes of water-rich material from beneath its icy shell. Neptune's moon, Triton, may be a captured object from the outer solar system and shows signs of active geology. These moons reveal that the planetary region is not a collection of simple spheres. It is a layered system of subworlds, many with histories as intricate as planets themselves. Dust also moves through the solar system, forming a faint zodiacal cloud that scatters sunlight. This material comes from comets, asteroid collisions, and the continual grinding down of small bodies, seen from dark places on Earth under suitable conditions. It produces the zodiacal light, a soft glow along the plane of the solar system. The presence of dust shows that the planetary region remains dynamic. Collisions continue, surfaces weather. Small particles drift inward under the subtle effect of solar radiation. Nothing in the system is perfectly unchanged. Even the calmest orbit exists within a setting of gradual evolution. Comets pass through this region as well, especially when their long orbits bring them inward from colder outer reservoirs. As a comet nears the Sun, heat causes some of its ices to turn directly into gas, a process called sublimation. Gas and dust stream away, forming a coma around the nucleus, and often one or more tails that point generally away from the Sun under the influence of radiation and the solar wind. These visitors connect the outer icy frontier to the brighter inner planetary realm. They carry ancient material inward and briefly become visible signs of the solar system's larger extent. The planetary region also contains invisible structures. Magnetic fields surround several planets. Radiation belts trap energetic charge particles. The Sun's gravity binds the whole region, while its light and particle outflow create changing conditions known collectively as space weather. Solar flares and coronal mass ejections can disturb planetary magnetospheres and atmospheres. Space between the planets is therefore not empty in a simple sense. It contains plasma, dust, radiation, and fields in continual interaction with solid worlds and gaseous envelopes. What makes this region feel ordered is not stillness, but regularity. The planets orbit in predictable periods. Seasons repeat where axial tilt allows them. Resonances stabilize some systems and disturb others in ways that can still be calculated. The broad arrangement reflects the memory of formation from a disk, then billions of years of mutual adjustment. The solar system is neither a machine in the rigid sense, nor a chaos without pattern. It is a gravitational society whose members keep long habits. In this central family of worlds, scale becomes easier to grasp but not small. Distances between planets are measured in tens, hundreds, or thousands of millions of kilometers. Light from the Sun takes minutes to reach Earth and hours to reach the outer planets. The giant worlds are large enough to contain many Earths, while the Sun itself could contain more than 1 million Earth-sized volumes. Yet compared with the galaxy, this entire ordered planetary province is tiny. It is a small bright arrangement around one ordinary star, intricate and spacious within itself, but only a modest inner chamber inside the far larger house of the universe. Around Earth, cosmic scale contracts again, but it does not become ordinary. The neighborhood of Earth and Moon is the smallest fully celestial region in this long descent from the edge of the observable universe. Yet even here, distance remains far beyond direct human bodily sense. Earth is a planet with a radius of a little more than 6,000 kilometers. The Moon is much smaller, with a radius of about 1,700 kilometers. Between them lies an average distance of about 384,000 kilometers. This gap is large enough that all the other planets are irrelevant to the immediate motion of the pair, yet small enough that the bond between them becomes one of the most intimate large-scale relationships in the solar system. The Moon does not circle Earth as a decorative companion fixed in one simple path. Earth and Moon are two bodies bound by gravity, each responding to the other. The Moon is much less massive, so Earth moves less, but both bodies orbit a shared center of mass. This center lies inside Earth, because Earth is so much heavier, yet not exactly at Earth's geometric center. The pair therefore behaves as a true two-body system within the larger gravity of the Sun. This is a subtle but important point. The Moon is not merely carried around passively. It and Earth form a gravitational partnership, balanced unevenly but precisely. The distance between them has made the Earth-Moon system one of the earliest laboratories of cosmic measurement. Long before the scale of galaxies is understood, the Moon provides a first celestial distance large enough to challenge instinct and small enough to be measured with growing accuracy. Ancient observers estimate its distance through geometry and eclipses. Later, astronomers refine that measure. In the modern age, laser ranging allows extraordinary precision. Reflectors left on the Moon by human missions return laser pulses sent from Earth. By timing the round trip of light, scientists measure the Earth-Moon distance to within a few centimeters. In this way, light itself becomes a ruler across near space. That light crossing takes a little more than 1 second in one direction. This simple fact helps transform the Moon from a bright disk in the sky into a physical world at a measurable remove. The Sun is minutes away in light travel time. The Moon is only a little more than 1 second away. This makes it both close and remote. It is close enough to dominate Earth's night sky and to have been reached by human beings. It is remote enough that no ordinary earthly motion bridges the gap easily. Even at the speed of a fast aircraft, the journey would take many days. Human closeness to the Moon depends not on small distance, but on extraordinary effort. The Moon's orbit is not a perfect circle. It is slightly elliptical, meaning that the distance varies over the course of an orbit. At its nearest, the Moon comes somewhat closer to Earth. At its farthest, it recedes by tens of thousands of kilometers. The change is enough to alter its apparent size in the sky, though only modestly to ordinary sight. This shifting distance reminds the observer that orbital motion is never a simple static ring. It is dynamic geometry, shaped by gravity, momentum, and the influences of other bodies, especially the Sun. The Earth-Moon system is also a record of long evolution. The leading explanation for the Moon's origin is the giant impact hypothesis. According to this model, early Earth is struck by a Mars-sized body during the violent era of planetary formation. Material from Earth's outer layers and from the impactor is thrown into orbit. Over time, this material gathers into the Moon. Observations of lunar rocks and the chemical kinship between Earth and Moon strongly support some version of this history. Though detailed aspects of the exact impact and the later mixing remain areas of active study, what matters here is that the Moon is not a captured stranger in the usual sense. It appears to form from the same event that reshapes the young Earth. Since then, the relationship continues to change. Tidal forces connect the two worlds. A tide is the response of a body to differences in gravity across its extent. The Moon's gravity pulls more strongly on the near side of Earth than on the far side. Earth's oceans respond visibly, but the solid planet also deforms slightly. These tidal bulges do not align perfectly with the Earth-Moon line, because Earth rotates faster than the Moon orbits. The result is a transfer of angular momentum. Earth's rotation gradually slows, and the Moon slowly moves outward. Measurements show that the Moon is receding from Earth by a few centimeters each year. This is slow enough to be invisible in a lifetime, yet certain enough to show that even the nearest great celestial relationship is not fixed. The Moon itself is tidally locked to Earth. This means it rotates once on its axis in the same time that it orbits Earth, so one hemisphere generally faces Earth at all times. This does not happen by accident. Over long periods, tidal interactions damp its rotation into this stable state. The same side therefore becomes the near side, while the far side remains hidden from direct earthly view until spacecraft reveal it. The near side and far side are not identical. The near side contains broad dark plains of ancient volcanic basalt, while the far side is more heavily cratered and brighter overall. The difference reflects early internal and geological history. not any special favour toward Earth's gaze. The region around Earth also includes layers of practical space shaped by gravity and motion. Satellites orbit at different altitudes. Some circle close in low Earth orbit, others occupy more distant paths. At about 36,000 kilometers above Earth's equator lies geostationary orbit, where a satellite can match Earth's rotation and appear fixed over one longitude. Beyond that lie broader cislunar trajectories, the region of space between Earth and Moon. The word cislunar means this side of the Moon, referring to the space extending from Earth outward to the lunar distance. It is within this region that human spaceflight first leaves the immediate neighbourhood of Earth and begins to enter a genuinely deeper local cosmos. Yet even cislunar space remains a tiny chamber compared with the rest of the solar system. The full Earth-Moon distance would fit many times between Earth and the Sun, and the whole Earth-Moon system is itself only a minute fragment of the Sun's domain, still, because it is the first great external distance that humanity measures, crosses, and inhabits by machine. It carries a special role in understanding scale. The Moon turns abstraction into encounter. It is not merely seen, it is orbited, touched, sampled, and timed by light. In this near celestial space, the universe becomes most legible without becoming small. The Earth-Moon system offers a measure of separation that can still be spoken in numbers simple enough to hold, yet vast enough to humble movement, duration, and human engineering. Earth circles beneath, the Moon circles beyond, and together they form a quiet gravitational pair suspended in sunlight. A near and ancient partnership that teaches how quickly familiar sky becomes real distance when measured honestly. From the Earth-Moon system, the scale of the universe can be translated into forms that the human mind approaches more easily, though never fully masters. The distances themselves do not shrink. What changes is the method of holding them. Instead of beginning with galaxies and horizons, attention rests on movement, travel time, and layered comparison. A kilometre on Earth can be walked. A journey across an ocean can be imagined through ships and aircraft. A trip to the Moon can be measured in days. From there, the ladder rises quickly. The purpose of this region is not to reduce the universe to something small, because it cannot be made small, but to place it alongside familiar measures and show how ordinary experience fails step by step. A person walking at a steady pace covers a few kilometres in an hour. A fast train crosses a country in hours. A jet aircraft crosses a continent in part of a day, and an ocean in less than one full rotation of Earth. These speeds feel impressive in daily life because human senses are built for landscapes, not planets. Yet when the scale widens even to near space, those same speeds become almost still. An aircraft flying continuously toward the Moon would need many days. And in practice, such a machine could not make the journey at all because the atmosphere ends and orbital mechanics take over. Human intuition built from roads, weather, and cities begins to lose its power almost immediately outside Earth. A rocket changes the scale, but only partly. The missions that carry human beings to the Moon take about 3 days to arrive. That seems swift compared with the age of the Earth-Moon system. Yet it is long enough to remind the traveller that near space is not near in the ordinary sense. The Moon is close enough to dominate the night sky, but not close enough to belong to ordinary movement. A light signal covers the gap in a little more than 1 second. A human journey takes days. This contrast between light and matter is one of the first great lessons in cosmic size. Light makes vast gaps seem navigable. Bodies moving with mass make them real again. The Sun stands much farther away. Light from the Sun reaches Earth in a little more than 8 minutes. This means that when sunlight touches the ground, it has already spent more than 8 minutes crossing space. If the sun were suddenly to vanish, Earth would continue receiving its last light for that interval. In human terms, 8 minutes is brief. In terms of distance, it corresponds to about 150 million kilometers. The mind learns here that time can function as a more useful measure than raw length. A light minute becomes more graspable than a string of digits, because time belongs to lived experience. Yet even this more intimate measure only partly helps. 8 minutes of light is still a gap no human vehicle crosses quickly. The outer planets stretch this method further. Light from the Sun takes tens of minutes to reach Jupiter and several hours to reach Neptune. A spacecraft launched from Earth needs years to arrive at the giant planets. Voyagers crossing the solar system make the outer planets feel both newly reachable and still profoundly distant. The path from Earth to Jupiter is not like a sea crossing. It is a multi-year fall and curve through gravity. A journey where planets themselves move along their orbits while the spacecraft travels. Travel inside the solar system already belongs less to ordinary motion than to celestial timing. Then the nearest star beyond the Sun stands at about 4 1/3 light years. This is the distance light itself needs more than 4 years to cross. Human technology has sent no crewed craft anywhere near such a journey. Even the fastest spacecraft launched so far would require many thousands of years to travel that far. Here comparison becomes sobering. If the Earth-Sun distance is treated as one step, the nearest star requires tens of thousands of such steps. The solar system, which already seems broad, becomes a tiny pool of light in a much larger darkness. The human mind often turns to scale models at this point. If the Sun were reduced to the size of a small fruit, Earth might be a tiny grain several meters away. Jupiter would be larger, placed farther out. Neptune would lie far across an open field. The nearest star in that same model would stand at a distance so great that the model could no longer fit inside a room, a building, or even a neighborhood. It would demand many hundreds of kilometers of separation. Such models are useful because they show that the emptiness between objects grows faster in importance than the objects themselves. The universe is not mainly a collection of things, it is a collection of intervals. The galaxy expands this lesson again. The Sun's orbit around the centre of the Milky Way takes about 230 million years. Human civilization in its written form occupies only a minute fraction of one such orbit. Even the age of the dinosaurs fits inside only part of a single galactic year. This comparison places biological and historical time inside a much larger celestial rhythm. The Milky Way spans about 100,000 light-years, meaning light needs 100,000 years to travel from one side of the bright disk to the other. At the speed of current spacecraft, crossing the galaxy would require time so long that individual cultures, languages, and species would lose meaning before the journey ended. Galaxies themselves are then separated by still greater gaps. Light from Andromeda takes about 2.5 million years to reach the Milky Way. The image of Andromeda seen today is a record from long before human beings exist in their present form. Looking deeper into the universe means looking further into the past. A distant galaxy is therefore not only far away, it is ancient light arriving late. The observable universe extends so far that its edge is measured not in millions but in tens of billions of light-years of present distance. At that point, comparison with travel becomes almost ceremonial. No human vehicle, no generation of civilizations, and no ordinary image of motion can carry meaning comfortably across such a measure. And yet comparison still has value. It shows where comprehension begins to fail. That failure is not weakness, it is information. It reveals that human senses evolve for forests, plains, rivers, and weather, not for galaxies or cosmic horizons. To understand the universe, The mind must rely on mathematics, instruments, and careful analogy. Travel time, light time, and scale models become bridges between instinct and reality. They do not make the cosmos familiar, but they keep it from becoming empty abstraction. In this translated view, the universe appears as a nested set of enlargements. A road becomes a continent becomes a planet becomes a lunar gap becomes the sun's distance. That distance becomes tiny inside the solar system, and the solar system becomes tiny inside the stars nearby. Nearby stars shrink within the galaxy shrinks within the larger web. At every step, the same lesson returns in quieter form. What seems large at one level becomes small at the next. Human understanding survives not by mastering the size, but by learning how scale changes the meaning of every measure beneath it. At the deepest inward point of this long descent through scale, the question changes. It is no longer only how large the universe is, but how that largeness is known at all. Size on cosmic scales cannot be measured with a single ruler or one direct view. No observer stands outside the universe to inspect its full form. No spacecraft crosses even a meaningful fraction of the distances involved. Knowledge must therefore be built in layers, each one reaching farther than the last, each one tied to forms of light, motion, geometry, and physical law that remain consistent across space. The scale of the universe is not guessed in one leap. It is assembled from many linked measures, each tested against the others. The nearest distances are measured most directly. Inside the solar system, radar and light travel time provide highly reliable values. A signal sent to a planet or spacecraft and reflected back gives distance through the measured speed of light. The Earth-Moon distance can be determined with laser pulses. Planetary motions are tracked with exquisite precision. At this level, cosmic size begins as careful timing. Light acts as a clock across space. This is the firm ground from which larger measures rise. Beyond the solar system, direct ranging becomes far harder, and geometry takes the next step. The most basic geometric method is stellar parallax. Parallax is the apparent shift in the position of a nearby object against a distant background when the observer changes location. On Earth, a finger held before the face appears to jump when viewed first with one eye and then the other. In astronomy, Earth's orbit provides the changing viewpoint. As Earth moves from one side of the Sun to the other over part of a year, a nearby star appears to shift slightly against much more distant stars. By measuring that tiny angle, astronomers calculate distance. The method is simple in principle and extremely demanding in practice because the shifts are so small. Modern space observatories have made parallax a strong foundation for distances to many stars within the Milky Way. From those stars, astronomers build the next layers through standard candles. A standard candle is an object whose true brightness is known or can be inferred. If the true brightness and the observed brightness are compared, distance can be determined. Cepheid variable stars are one important example. These stars brighten and dim in a regular pattern, and the length of that pattern is related to their true luminosity, meaning the total amount of light they emit. By measuring the period of a Cepheid and comparing its known luminosity with how bright it appears from Earth, astronomers estimate how far away it is. Cepheids extend the distance scale well beyond parallax and help measure nearby galaxies. Farther still, Type 1, a supernovae provide another powerful rung. A supernova is the violent explosion of a star. Type 1a supernovae arise under special conditions involving white dwarfs and tend to reach similar peak brightnesses, making them useful as standardizable candles. They can be seen across vast distances, far beyond individual Cepheid stars. by calibrating them with nearer distance measures. Astronomers use them to trace the scale of the wider universe and the history of cosmic expansion. Observations of these supernovae play a major role in the discovery that the expansion of the universe is accelerating, a result that points toward the influence of dark energy, the name given to the unknown cause of that acceleration. Galaxies themselves also provide clues to distance and size. Their redshift, the stretching of light toward longer wavelengths, reveals how strongly the expansion of space affects the light during its journey. In general, the greater the redshift, the farther the galaxy lies and the earlier in cosmic history its light is being seen. But redshift alone does not act like a simple tape measure at all distances. It must be interpreted through a cosmological model, a mathematical description of how the universe expands over time and what it contains. This model includes ordinary matter, dark matter, radiation, and dark energy. When astronomers combine redshift measurements with calibrated distances from supernovae and other methods, they infer the large-scale expansion history of the universe. The cosmic microwave background adds a still deeper layer. Its delicate pattern of temperature variations provides information about the geometry, contents, and age of the observable universe. By fitting the observed pattern to cosmological models, astronomers estimate key parameters such as the age of the universe and its large-scale curvature. Observations indicate that the observable universe is very nearly flat on large scales. This does not prove that the full universe is infinite, but it does place strong limits on how tightly it could be curved. A universe with strong overall curvature would leave different imprints in the ancient light than what is observed. This is where the limits of knowing size become most important. The observable universe has a measured size in the sense that its present radius can be estimated from the age of the universe, the speed of light, and the expansion history of space. That observable radius is about 46 billion light-years. This value is not a rough poetic statement. It is a model-based scientific estimate with strong observational support. Yet it describes only the part of the universe from which light has had time to reach the present observer. It does not reveal the full extent of all existence. Beyond the observable universe, uncertainty begins in earnest. Space may continue infinitely. It may also be finite, but so much larger than the observable part that its boundary lies forever beyond view. Observations indicate that if the full universe is finite, it must be very much larger than the observable region. But no direct evidence currently reveals its total size. No light arrives from beyond the cosmic horizon, and no present method can bypass that limit. This uncertainty is not a gap waiting only for better telescopes in the ordinary sense. It is tied to the basic structure of causality in an expanding universe. Some regions are not merely unseen for now, they may be permanently beyond contact. Even within the observable universe, some details remain under refinement. One important example is the Hubble tension, the difference between some measurements of the current expansion rate derived from the early universe and others derived from more nearby observations. The tension does not erase the basic picture of expansion, nor does it make the universe's scale unknown in a general sense. But it reminds astronomers that precision cosmology still contains unresolved issues. The framework is strong, yet not complete in every detail. There are also quantities that are inferred more than directly measured, such as the exact nature of dark matter and dark energy. Their existence is supported by multiple lines of evidence, but their physical identity remains uncertain, because they influence the growth and expansion of the universe. Uncertainty about them also shapes the deepest interpretation of cosmic size and fate. Observations indicate what they do. it remains uncertain what they are in a more fundamental sense. So the final boundary is not merely a horizon in space, it is a horizon in knowledge. Astronomers know a great deal about the size of the observable universe, the age of cosmic expansion, and the layered distances that lead from the moon to the earliest light. They measure nearby space directly, map the galaxy with geometry, gauge remote galaxies with standard candles, and test the whole framework against ancient radiation. This chain of knowing is one of the most careful achievements in science. Yet when the question becomes the total size of all that exists, certainty gives way to disciplined restraint. Observations indicate a universe at least vastly larger than the visible part. It remains uncertain whether there is any final edge at all. The measured universe settles at last into quiet proportion. The moon circles Earth. Earth circles the sun. The sun moves within the Milky Way. The Milky Way drifts among neighbouring galaxies. Those galaxies belong to larger gatherings, and those gatherings thread the wider web that stretches across the observable cosmos. At each scale, what first appears central becomes local, and what first appears vast becomes one part of something larger. The mind does not overcome this immensity. It learns to rest beside it. Observations reveal a universe with a visible radius of about 46 billion light-years, filled not mainly by things, but by distance. Light carries the history of that distance inward, arriving from stars, galaxies, and the first transparent age of the cosmos. Gravity shapes the patterns. Expansion stretches the whole. Dark matter adds weight without shining. Dark energy widens the spaces further still. Much is known with care. Much remains hidden beyond the horizon where light has not had time to arrive. In the end, the size of the universe is not only a number, it is a relationship between time, light, motion, and limit. It is the long delay between event and sight. It is the gentle truth that every night sky is also a record of the past. It is the quiet fact that home exists inside layers of structure so large that language must borrow from light years, redshift, and ancient radiation just to speak at all. And yet the great scale does not erase the small. A human life remains brief, local, and warm beneath a thin atmosphere on one ordinary planet. The universe does not become less beautiful because it is too large to finish measuring. It becomes calmer. Its immensity leaves room for patience, for careful thought, and for silence. The stars remain where they are. The galaxies continue their slow recession, and the unseen distances hold steady around every known thing.